16 years is a long time in any man's language. That's how long it's been since we devoted a Master Tech session to the cooling system. The basics of cooling systems haven't really changed much during that time, but there are some new problems that we run into occasionally. Mainly because we expect so much more from the system than we used to. Bigger engines, heavy accessory load, tougher driving conditions all add to the heat problem. Let's eavesdrop on Al and Jimmy as they discuss some of the points of cooling systems and the problems we all run into once in a while.
Hi, Tech. I was just about to give Jimmy a rundown on the cooling system. He was telling me that cooling complaints always put him in a sweat. So I figured it was because he needed to understand them better.
A good possibility, Al. One thing to remember, Jim, about any job you're working at, if you understand how things are supposed to work, it's a lot easier to figure out why they're not working that way.
I'm all ears, man. Educate me.
Well, first of all, Jim, the cooling system has a big job to do. Combustion temperatures in the cylinders can run in the neighborhood of 3,000 degrees or more, even during normal driving conditions, and that's a lot of heat. About 1/3 of that heat is converted to driving power. Possibly another third is expelled in the exhaust gas. The remaining third is absorbed by the coolant flowing through the heads, block, and manifold.
Keep in mind, Jim, that the cooling system does more than just get rid of the heat from combustion.
Right, Tech. In fact, the name heat control system might fit just as well as cooling system. It helps the engine warm up quickly and evenly, and then keeps it at an even temperature to get the most out of every drop of fuel. As soon as the engine is started, heat distribution becomes important. Hot spots develop around valves and cylinders. The coolant, circulating through the heads and block, carries the heat away from these areas and distributes it to other cooler areas, so the engine warm-up is more uniform. Now, during this warm-up period, the coolant bypasses the radiator and carries all its heat back into the engine until the coolant reaches a temperature of about 180.
That's when the thermostat opens, right?
You're not so fast, Jim. It starts to open at 180, give or take about 5 degrees. When you're testing a thermostat, the valve should start to move somewhere between 175 and 185. As the temperature goes up, it'll open gradually until it's wide open at about 205 degrees.
Well, that's a good point to note, Tech.
When the thermostat starts to open, the radiator starts working with the thermostat to control the engine temperature. The radiator takes enough heat out of the coolant to keep the engine from overheating, and the thermostat keeps enough heat in the engine to maintain the best operating temperature. Just as the coolant carries the excess heat out of the engine, air moving through the radiator carries heat away from it, forcing it out of the engine compartment and underneath the car.
Now that brings up a very important point, Al. The size, shape, and speed of the fan. It has to move enough air to do the job, but we want to avoid a lot of unnecessary noise at high engine speed.
Well, that sounds like a big order.
It is, Jim, but our fluid coupling fan drives do just that. They're used on some of the air-conditioned cars. You know, air conditioning puts quite a load on the cooling system, especially at low speeds and in heavy traffic.
I can see how it would, Al, with that condenser pouring hot air right into the radiator. But how does a fluid fan drive get around the problem?
Well, it gives maximum airflow at low engine speed, but limits the top speed of the fan to get away from the noise. Here's how it works. To get the maximum airflow at low engine RPM, we use a 7-blade fan and a smaller pulley to increase the fan's speed.
That increases the pump speed, too. So the pump used with this unit has a smaller impeller. Otherwise, you'd get too much pressure and probably blow off the heater hoses or blow out the core plugs.
Now, that's easy to remember, Tech. Small pulley, small pump. But didn't you say that a high-capacity fan would be noisy at high speeds, Al?
I also said that we are going to limit the top speed of the fan, and we do that by driving the fan through a fluid coupling. The small pulley gives a higher drive ratio and gets the fan up to its maximum speed at lower engine speed than a conventional solid drive. At this maximum speed, called the terminal speed, the fan exerts enough resistance to cause the coupling to slip. Increasing engine speed beyond this point will not increase fan speed.
Actually, Jim, we have two kinds of fluid fan drives, the silent flight and the temperature-sensitive type. Both of these fluid drives limit the top speed of the fan. How about explaining what the temperature-sensitive type does besides controlling top fan speed, Al?
Okay, Tech. When the engine and radiator are cold and air circulation isn't needed, the temperature-sensitive coupling just idles, and the fan turns slowly. As radiator heat warms up the drive unit, a temperature-sensitive control gradually engages the coupling, and it operates just like the silent flight unit to limit terminal speed. There's one thing everyone should understand about these temperature-sensitive units. There's nothing wrong if the fan runs full speed when the car is first started in cold weather. That's because the oil in the coupling thickens with the cold, but it'll thin out after the car is driven a short way and the fan will slow down.
Here's an important safety tip. Don't ever lock up either type of fluid fan drive to get more cooling, even for heavy-duty operating conditions such as hauling a trailer with an air-conditioned car.
Good point, Tech. The fans used with fluid drives are designed to provide high airflow at low engine speed. If they're forced to go faster than the terminal speed, they'll set up stresses that can get strong enough to tear them apart. If an owner is going to haul a big trailer, he should have a car equipped with a special heavy-duty trailer towing package. It has a solid fan drive and a heavy-duty fan.
That's right, Al. But there's more to the heavy-duty package than fans and fan drives. There's more about fan shrouds, heavy-duty radiator cores, and other heavy-duty equipment in the reference book.
Say, Al, didn't I hear you talking about a heater complaint the other day? Who needs heat this time of year?
Nobody needs heat in hot weather, Jim. That's why we got the complaint. The problem actually started last winter, right, Al?
Right, Tech. The owner decided to be his own mechanic and set the water valve control cable to open the valve farther. Well, that didn't hurt a thing as long as the weather was cold. When it warmed up, though, it turned out that he couldn't shut the valve off all the way, so he got a hot foot until we readjusted the control. You can get the same problem if a small particle of rust or dirt lodges under the flow valve seat and holds it open. Usually, if you open the valve all the way and race the engine a few times, the coolant flow will clear it away.
Speaking of coolant flow, anytime you're working on a heater, be sure you get the hoses back the way they're supposed to be. Otherwise, you'll reverse the flow through the flow control valve.
Well, how can that make any difference? As long as the valve is closed, no coolant can flow. And when it's open, the coolant still goes through the heater core, right?
Not quite, Jim. You see, the normal coolant flow through the valve tends to open the valve, and the lever that opens the valve is spring-loaded in the same direction, with a stop clip to prevent the coolant flow from opening the valve all the way. If the hoses are reversed, the flow will try to close the valve against the spring. As engine speed increases, the flow speed also increases until it gets strong enough to force the valve shut and cut down on passenger heat.
The valve bounces back and forth between the spring force and the coolant flow. You'll be able to spot it easily at about 55 miles an hour with an intermediate heat setting. It raps pretty loud.
Speaking of heater complaints, Tech, it's surprising how many no-heat situations are caused by someone taking out the thermostat.
That's right. A lot of backyard mechanics still think that a thermostat isn't needed in the summer. They forget that an engine is designed to perform best at a certain operating temperature. The thermostat's job is to get the engine up to that operating temperature as quickly as possible. For instance, the thermostat should have the engine up to operating temperature by the time the choke cuts out. If the engine is not thoroughly warmed up when the choke goes off, performance will not be good. Here's another thing I'd better mention right about now. Somebody better flip the record before we have an overheated needle.
Here's something I don't quite understand. Why do our pressure caps have this type of vent valve? I know some of our competitors use a different type of cap.
That's a good question, Jim. And it brings up an important feature of our cooling system. Under normal driving conditions, the vent valve in the cap hangs down and is open. The cooling system operates at atmospheric pressure. This eliminates unnecessary pressure and strain on the radiator core and hoses, so they last longer.
Well, then why have a pressure cap?
The pressure cap prevents loss of coolant, Jim. A surge of coolant into the upper tank of the radiator closes the vent valve, and the system becomes a closed or pressurized system. For example, under severe operating conditions, the coolant may reach its boiling point. Then steam formed in the engine water jacket pushes coolant into the radiator. This, of course, closes the vent valve, and the entire cooling system is pressurized. As soon as the system is under pressure, the boiling point of the coolant is raised. As long as the heavy heat load is on the engine, the cooling system operates under pressure at temperatures above the normal boiling point, but without loss of coolant.
Oh, I get it now. If the pressure should ever get too high, higher than the pressure rating of the radiator cap, the pressure cap would act as a safety valve and open.
Exactly right, Jim. Now, here's something else that vent valve in the cap does. When the coolant starts to cool off, it contracts, pulling air in through the vent valve to keep from creating a vacuum. If that valve doesn't open, the vacuum can get strong enough to collapse the hoses. So always check the vent valve. Take a good look at the gasket, too. If it looks like it's starting to deteriorate, better put on a new cap.
Checking the pressure cap is a simple but very important step in cooling system maintenance. If it doesn't release at the specified pressure, the system can build up enough pressure to cause a hose blow-off, blow the core plugs, or even damage the heater or radiator core. The standard cap should hold pressure to between 12 and 15 psi. On air-conditioned cars, the cap should hold 15 to 16 pounds. To pressure test the cooling system, run the engine long enough to bring the coolant up to operating temperature, then pressurize the system to 16 pounds. If the system will not hold the pressure, check for external leaks first.
If you don't find any external leaks, there must be internal leaks, which usually won't show up on a visual inspection. However, a leak into the engine oil may show up on the dipstick. Another possibility is a leak between the radiator and the transmission oil cooler. An oil cooler leak can be a two-way leak.
How so?
Well, when the engine is running, the pressure in the oil cooler lines gets as high as 30 psi. The difference in pressure will force some oil into the coolant. On the other hand, some coolant may enter the transmission fluid when the engine is stopped. That can play hob with the clutch and band friction facings in the transmission. There's one more kind of leak I'd like to talk about: combustion leaks. If the head gasket is leaking between a cylinder and one of the water passages, part of the exhaust fumes will be forced into the coolant.
Well, how do you find out if this is happening?
You can check this by using the block check tester. If it shows combustion fumes, you can determine which side the leak is on in a V8 by removing all the spark plugs from one bank and running the engine for a short time. If the fumes don't appear on the tester with the plugs out, you'll know the leak is on that side.
That's a good tip, Al. And here's another. When you pull the plugs, ground the plug wires and don't run the engine with plugs removed any longer than necessary. The reference book explains how to use the block check kit.
I'd appreciate hearing the straight story on the ethylene glycol antifreeze we're using now. How long can we use it without draining and flushing?
Well, I guess it could get a little bit confusing. How about it, Al?
First of all, we recommend that antifreeze changes be made in the fall of every year. A charge of Chrysler or Ethylene glycol antifreeze should be good through the winter and the following summer until time for the next fall service. It's good for at least 12 months and may be used a little longer. For example, let's say the cooling system was serviced in January 1964. It won't be necessary to drain and refill until the fall of 1965. Air-conditioned cars, except those equipped with cool air, need year-round protection down to at least 15 degrees above to keep the heater core from freezing.
Cars without antifreeze should have Mopar or Crico rust resistor during the summer to prevent corrosion. A good rust resistor also keeps the coolant from foaming. If there's a lot of foam in the system, you're liable to lose some coolant.
Right, Tech. Keeping the system clean and foam-free is one of the most important parts of cooling system service. When it's time to winterize the car, drain and flush the radiator and block to get all the cooling system contaminants out. When you refill the system, be sure to run the engine long enough to open the thermostat. Then rev the engine up a few times to get the air and steam pockets out of the heads, block, and manifold. You'll probably have to add some water after they're cleared.
But don't fill the radiator all the way to the top. You need about 1.25 inches airspace to allow for coolant expansion.
Expansion will force any excess coolant out through the overflow. It doesn't cause any harm to the system, but it can upset an owner.
Hold on a minute. There's a little item there called a pressure cap that's supposed to stop that coolant from going out the overflow.
Good thinking, Jim. But you see, the flow is not fast enough to close the vent valve, so the coolant sneaks right past it.
Here's another little tip that can save a lot of time, Jim. Sometimes an overheating complaint turns out to be merely gauge or sending unit trouble. The first step is to see if the fuel gauge is also acting up. If it is, check the voltage limiter and the instrument cluster ground. If the fuel gauge is okay,
then I can use the gauge tester to find out whether the culprit is the temperature gauge or the sending unit, right?
you sure can, Jim. Substitute the tester for the sending unit to check out the gauge circuit. If the gauge circuit checks out okay, then it's a pretty sure bet that the sending unit is bad and should be replaced. Now here's another possibility. The temperature gauge operates according to variations in resistance. The sending unit is simply a resistor that allows more current to flow as it warms up. So if the gauge always reads too high, we can bring it down where it belongs by adding resistance to the circuit. Makes sense, doesn't it?
It sure does, Al. How much resistance should be added?
If the indicator goes higher than 2/3 through the normal bar when the tank temperature is 190, add a 1-watt resistor in the circuit. That's 2.7 ohms.
You can get one of those at your neighborhood radio shop. Be sure to solder the splice and tape it to avoid grounding the circuit. Now, before we run out of time, Al, let's talk about belts and noises.
Good idea, Tech. The biggest offender, naturally, is the loose belt. But any belt problem can be a strong source of annoyance to an owner. Usually, though, it's easy to get rid of. To isolate belt noises from water pump squeal, pour a little water on the belt while it's running. If the squeal stops, check the belt condition and pulley alignment. Try a little Mopar Sil Glide lubricant to get rid of a squeal caused by belt glaze. If a loose belt is neglected, that constant slipping really shines it up. Retightening the belt won't stop it without some lube. You can check pulley alignment by placing a straight edge against the side of the pulley and along the belt. The straight edge should be parallel with the belt.
Even if the noise turns out to be a pump squeal, try Mopar or Chrysler water pump lube before replacing the pump. It might take a couple of 100 miles of driving for the lube to take effect and quiet the seal down. It looks like we've worked our way through side 2 of the record, so we'll leave you with the reference book and this thought. Cooling systems, like any other system in the car, have a specific function and definite operating characteristics. Understanding the system will go a long way in helping you to keep it cool.